today is chapter 11. Here are the topics we're going to discuss today: angular velocity and angular acceleration vectors. The torque is a vector. These are all the results of cross products, torque and angular momentum. And we'll talk about gyroscopes at the end. I have a big giant gyroscope here. You may have seen me on the pre-class video with the tiny little one. I have the bigger one. But the way I want to start actually is I want to talk about cars. And there are three kinds of cars that you can buy: AWD, FWD, and RWD, meaning I guess an all-wheel drive, like a Subaru or a Tesla or something, will have the engine connected to and driving all four wheels. And FWD means that the front two wheels are connected to the engine, and when you step on the gas, those are forced to rotate, whereas the back two wheels are just freely rotating, so they're greased up, but they just roll along. And RWD, rear wheel drive, the rear wheels are connected to the engine, but the front wheels are just free to rotate. And probably 90% of the cars that you can buy are FWD. It's just cheaper to manufacture these. It's not really safer, but it's safer than rear wheel drive because there's usually more normal force on the front two wheels because the engine is up at the front and the engine is heavier than usually whatever you have in your trunk. So the question I want to ask, and should be on your Learning Catalytics screen right now, is this. So remember last time we said that there's this external force of static friction which is somehow driving this car. So you step on the gas, and I believe the function of the engine is to create a torque on your front two wheels. And I've drawn it there, torque engine, and the little lowercase tau is your Greek letter. So there's a force of static friction from the road on your front tires. Which direction is it? Forwards, same direction the car is accelerating, or backwards? Once you've thought about it, maybe just quickly check with your neighbor to make sure you're both voting the same way. Try to convince your neighbor. So the survey says about 61% of you voted correctly. So it's a bit weird. You'd think of friction as slowing something down, but in this case, the friction is actually what's speeding it up. And remember, that's what we discussed, I guess, last Wednesday, which is we said that there's got to be some external force acting on the car to get it accelerating, and that has to be static friction. And the way I like to remember this stuff is I think about which way would it slip if there was no friction. And then the static friction is what is preventing those two surfaces from slipping. So you step on the gas, and it makes the wheel want to go like that, right? So if it was slipping, it would be slipping, backwards. And so what the road does is it prevents it from slipping by pushing it forwards. Okay? That's where that's coming from. Next question, very similar to the question you just answered. Oops. Wrong. There we go. But I want to ask you about the rear wheels. That's all. The ones that are not at all hooked to the engine. Is there a force of static friction on those free to rotate wheels? And if so, is it forwards or is it backwards? Think about that. Again, try to convince your neighbor. Somebody told me that it doesn't work convincing my neighbor because I can never convince him. But I have found, in my experience, sometimes I get an answer, I try to convince somebody of it, and about halfway through my explanation, I realized, yeah, actually I think I'm wrong. I've just convinced myself the opposite of what I originally thought. So, which is good. Sometimes articulating your thoughts makes you think about them even more. So I'll give you 1 minute. This one was very, very split. But the one I like is backwards. Bit weird. But once again, I would like you to think about why is the back wheel rotating? Well, or what's happening with it? Why is it not rotating? Or why is it rotating, I guess? So if it's not connected to the engine, it's just being dragged along. So if it was a frictionless surface, it would go like this without rotating. But instead, it's a friction-y surface, so it has to rotate. So I think that this is the sliding motion that would happen if there was no friction forwards. So the friction from the ground on the wheel has to be backwards. It's a very small force because all it has to do is just rotate that back wheel, and if the back wheel is greased, then all you have to do is just provide enough torque to rotate that wheel. Whereas on the front wheel, there's a very, very large forward force of static friction. So they're not the same at all. The force on this one would be huge, and the force on this one would be just a little bit backwards. It's sort of hard to even show it there. But so the net static friction force is definitely forward. So some student comments from this morning, since static friction is always associated with not moving, is it impossible for static friction to do work? This is a great question. The answer is that's actually correct. When you have the force of static friction on something that's rotating, be it a yo-yo or be it a wheel, then the point of contact between the ground and the rotating object is at rest. And so it can't do work because there's no instantaneous displacement. So then the question is, if the net force causing a car to move forward is static friction, then what force is doing the work on the car? And the answer is that the car is doing work on itself. So certainly there's not, you step on the gas, it's not like the earth is transferring energy up into the car to get it moving. The energy is coming from the chemical energy in the gasoline. The gasoline is being combusted and creating carbon dioxide and water vapor, and then that's causing that front wheel to have angular acceleration, and then the car moves forward, and so the energy gets into the car. And what the road does with static friction is it provides this constraint, rolling without slipping. It's a constraint that if the wheel is turning, then the whole car moves. And it provides momentum, but does not transfer energy. It's a bit weird. Let's move right along. So now we're getting into all this vector stuff. And basic idea is that we started the whole course talking about one-dimensional motion with scalar velocity v and, well, force F. That's one way of looking at things. And a more general understanding of motion requires these vectors, v now with instead of v with no arrow on it, we put an arrow on it, and F we put an arrow on it. And this means we're specifying not only magnitude, but also direction. So similarly, we've been talking about omega as if it's a scalar. We've talked about clockwise and counterclockwise. But what if the plane of rotation is changed around? Like it could be rotating, that's I guess a counterclockwise rotation, but it could be viewed from above or this way. Actually, this is counterclockwise, but if I turn it right around, it becomes clockwise, right? So it's a vector. Let's put little arrows on these, and we're going to use some conventions, which are historical and don't really come from anywhere, but it's called the right-hand rule. The angular velocity vector has a magnitude of the angular velocity in radians per second. So that omega is still the same 2 pi over period that it was before, and we can write that down. So omega equals 2 pi over t, the period. So that's still our equation for the magnitude. But now, you want to know what the direction is? Well, you use your right hand. And I even brought a giant right hand. So, put it in there. and you curl your fingers the way they would naturally curl if you have normal knuckles, and that's the direction that the thing is rotating. So if the thingy is rotating like this, for example, then you curl your fingers in the direction of the rotation, and then you stick your thumb up like you're hitchhiking, and that's the direction of the omega vector. So it's perpendicular to the actual motion, which is a bit weird. The actual motion is all, in the plane of the rotation, right? But you take the omega vector and put it perpendicular. Okay? So, like if it was rotating the other way, I would have to actually flip my hand around for my fingers to curve the right way, and now it's going out that way. Follow me? Okay. And this gets into cross-product stuff. Cross-product of two vectors is different than the dot product. So we had dot product of two vectors, which creates a scalar product. And now we have a different way to multiply two vectors. Giving a vector is called the cross product. And it's also different in the sense that with a dot product, it was maximum when the two vectors were parallel, and went down to 0 when the two vectors were perpendicular. That was, for example, work. When we did work as force dot with the distance. If the force is perpendicular to the displacement, then you're doing 0 work. Well, it's just the reverse with a cross product. Cross product is actually 0 when the vectors are parallel, and then becomes maximum when they are perpendicular. So there's a sine of alpha, where alpha is the angle between the two vectors. A times b times sine of alpha. So, and remember that sine, this is alpha, goes like this. So it's actually maximum at the 90 degrees, or 270, but 0 when they're parallel or anti-parallel at 0 or 180. And you use the right-hand rule, so that red vector is perpendicular to both of the blue vectors, red being the cross product and blue vectors being the two things you're producting. And then to figure out which way that red vector goes, it's perpendicular to the plane of the two original vectors. You use one of these various right-hand rules. And I'll tell you 3 completely equivalent right-hand rules, and then you just need to choose which one is your personal favorite. So the first one on the left says that you take your thumb and put it in the direction of A. You're trying to find the direction of A cross B. And then you put your index finger, your pointy finger, in the direction of B. So maybe into the page. And then you flip the bird with your middle finger, and that's the direction of A cross B. So that's like right-hand rule for cross product number 1. The middle one is the one I like to use, which is you, first of all, put all your 4 fingers in the direction of A, the thing you're gonna cross multiply, and then you bend your fingers in the direction of B, the thing you're cross B, and then your thumb points in the direction of that product. So the middle one's my favorite. And then the last one I call the peanut butter jar lid rule, which is you do A, which is the direction the lid is, and then cross B, the direction you're turning the lid to, and then the cross product is the direction the lid actually goes. So if you're tightening it, it goes down, so that's right. And if you're loosening it, it goes up, and so that's also right. So if you eat a lot of peanut butter, maybe that's your favorite one on the right. And we'll do a learning catalytics in a minute, so let's talk about where it comes up. First, it comes up twice. First for torque, and then for angular momentum. Torque. This is a messy little slide here. Torque, we defined earlier the magnitude of torque as being RF sine phi. It's actually the cross product. Somebody pointed this out here. It's torque vector is equal to R vector cross F vector. This is a much more useful and sort of general way of defining torque. And then torque is going to be in the direction of the change of the angular momentum vector. It's the only way we're ever going to understand this gyroscope is if we do things in 3D. Example, here is a wrench, and it's attached right there to a nut. If you're pushing the force down, well then R starts at the rotation axis and goes to the point where you're applying the force, and then cross F, the direction of the force. So R cross F, whatever way you want to do it, is going to be out of the page in this case. Let me do another question. There won't be an image on your phone, because I didn't have time to upload it, but let's put the image up on the board here. So this could happen to you someday. You could be driving along, and then boom, 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 you blow a flat tire. Perhaps your back left wheel. Well, you should call CAA, right? But the other thing you can do, if, I don't know, if you have the time, is there is a spare tire somewhere in your car. Every car has to have one. Might be in the hatchback somewhere, sometimes underneath where you put your stuff. Sometimes it's attached under the car. You've got to find it, but it's somewhere. And there's instructions. There's also a little jack which can lift up your car, and there's a big wrench. So what you need to do is actually jack up your car, take off the wheel, and put on the little spare wheel, which looks like this. And then you can drive for like up to a day, take it to a garage, and get them to fix it properly. And it takes like 15 minutes, whereas you might be waiting for 2 hours for CAA. So, but the trick is, these lug nuts are put on in a shop by Pneumatic Drill, and they're really on there really tight. And so what this lady's doing is exactly what you actually need to do. Before you jack up the car, you got to loosen all these 5 nuts, and you kind of have to attach the wrench and then jump on it to get it to turn, or kick it kind of down. And you do that for all 5 till they're all loose, then jack your car up. You don't want to do that while the car is jacked up, because you could knock it off the jack and injure yourself. But while the car is on the floor, loosen all 5 nuts, then jack it up, then take them the rest of the way off and swap out the new wheel. Anyway, it's got nothing to do with the question. I just want you to do R cross F. I'll give you a minute. And survey says, yeah, so most people are saying F, and I think that's right. So the way I would draw it, just to draw it here, that's the like rotation axis that you're trying to turn. This is the R vector, and then this is the F vector. Okay, so again, you can kind of try to do it. I do it, oops, this is R cross F equals right up at you, okay? And you can kind of draw it like that. So this is out of the page, and then this is into the page. I don't know if you've ever seen these two things, but if you put X, then it means in, and if you put a dot, it means out. And the way I try to remember it is that if this was like an arrow, and it was coming right towards you, then the pointy end would be right in the middle, so that's a dot. But if it had feathers on the back, then you looked at this, or a dart, perhaps. A dart going down, I should bring a dart. It would look, you would see the X in those feathers, right? So X means into the page, circle means out of the page. Okay, so well done. And next thing, the reason we have vector torque is because we have vector angular momentum. And a particle of mass m moving in some direction will have a momentum vector in the direction of its velocity, and it will have an angular momentum relative to the origin if you take r cross p. L equals r cross p. So any object, you can define both its momentum, m times v, and you can define its angular momentum about some axis, r cross p, where r is just the position of that particle relative to some origin. And the reason we did this is because if you take the time derivative of that angular momentum, then you get the torque. Just turn down the brightness a little bit. Hopefully you can see it. dl by dt is equal to the net torque. So this was actually how Wolfson originally introduced Newton's second laws. He said, recall, he said that dp by dt is equal to F net. So this is the analogy to that in linear. The The time derivative of the momentum is equal to the net force. Also, the time derivative of the angular momentum is equal to the net torque. Torque will cause angular momentum to change. So it's a more general way of stating this Newton's second law for rotation, which is that torque net is equal to the I times alpha. Similar. Okay. And then, so that's a particle. If you have a rigid body made up of many particles, then we can add the angular momenta of all the particles forming the object. So if the object is now on a fixed axle, or if it's rotating around axis of symmetry, it can be shown that L is equal to I times omega, I being the rotational inertia. And it's still the case that any net torque will cause a change in this L vector, rate of change of the L vector. It's super useful. And just put this up. This also follows with our analogy, is that P equals M times V, L is equal to I times omega. For omega now, use the right-hand rule to find the direction it's rotating. And this is a pretty easy one. One more learning catalytics, which is just what is the angular momentum of the wheels? What direction? Be 1 minute to discuss. I think that it's going to be something like this, omega. So I'm going to curl my fingers in the direction of omega. We sort of started with this, and so my thumb has to point down out of the page. So omega, sorry, into the page, right? E. Is that right? Yeah, good. So that's good. So next thing, I'm getting ready to do this crazy chair thing, which is that if you have no net external torques, then the angular momentum is constant. Okay? And this goes back to that figure skater thing, is that, remember that, once again, L is equal to I times omega. Normally you would think of I as being a constant. It was mr squared for a particle. For a solid disk, it was 1/2 mr squared. But if you have an object which is deformable, like a figure skater, or me, for example, then I can actually change. And then if L is constant, you have to adjust omega to compensate. So here's a picture of what we're going to try to do as a demo. Idea being that if I, which is for these masses, is going to be mr squared for this mass and for this mass, where r is this distance, mr squared. If that's large, from holding masses outwards, then I is large and you have a small omega. If you decrease I, then I've increased the font of omega. Okay, so I goes down, and omega goes up. That's this whole idea. So we can try it. I fear this demo a little bit because I get really dizzy, but it's important. Yeah, if I really injure myself, I'm sure somebody will call 911. So, okay. All right, so start like this, get myself going, bring the masses in, bring the masses out. Slows down, bring the masses in, bring the masses out. So here I have a large rotational inertia, and here I have a small rotational inertia. But there's no net external torque, so the omega has to compensate. Okay, good. Okay, I'm good. Perfectly good. All right, so then another fun thing we can do is, since again, if I sit on this thing, there's no net external torques, then me and this wheel should always have the same angular momentum. So let's spin this. I'm sure am I spinning it? I'm spinning it clockwise as viewed from above. So really fast. So right now, the system has angular momentum clockwise as viewed from above. Let me bring my foot up off the ground now. So if I switch the angular momentum of this, well now I'm rotating clockwise as viewed from above, and the wheel is counterclockwise as viewed from above. If I flip it, I'll stop. Almost. Okay. We have to, there you go, hello. We have to have a total angular momentum which is clockwise as viewed from above. So if I flip this wheel around, then I have to start rotating clockwise as viewed from above because the wheel is now going the wrong way. You got me? And then I can stop once I get to the right thing. Stop. There's a little bit of external torque which messes this up, which I guess is caused from some friction in the axle there. Okay, that's enough spinning. I think next we're going to do an example. This is a typical kind of question that comes up on the final exams and stuff. A 20 centimeter, 2 kilogram solid disc is rotating at 200 RPM. So we can draw it. So we like to draw a diagram. I'm going to draw it like this. And it's going around like this. Omega, so this is M1, is equal to 2 kilograms. And omega initial is 200 RPM. A 20 centimeter diameter, 1 kilogram circular loop is dropped straight down onto the rotating disc. It's a little harder to draw, but I'll do my best. So it's a loop, whatever the heck that means. I think like a hoop. So it's empty in the middle. You kind of picture it? I'm not an artist, but you got the basic idea. Anyway, it goes down. It's originally, so let's call this M2, is 1 kilogram, and omega initial is 0. It's not rotating. Friction causes the loop to accelerate until it is riding on the disc. So what this is this is a totally inelastic collision because originally these two things are moving relative to each other, and then when they collide, they stick together. So there'll be some kinetic energy lost, but the momentum will be the same. So there's no net external torque, and so therefore L is conserved, angular momentum. That's how this is going to go. So, and remember that R is equal to D over 2 is equal to 0.1 meters, because it's 20 centimeters diameter. So I guess I1 is going to be equal to the M1 times R squared, but it's going to be a half because it's a solid disk. And that would be something that you're given. And then I2 is equal to just M2 times R squared, because that's a hoop. The hoop is the one that's most like a particle, so it doesn't have a fraction out in front of it, because almost all the mass is just concentrated at a distance r. And so then, our strategy is to just say that L initial equals L final. So initially, and we can, L1 initial plus L2 initial equals L1 final plus L2 final. So L1 was the one that was rotating, and L2 was the one that's not rotating, so that one's 0. So you've got 1/2 M1 R squared times omega initial is equal to L1 final, which is 1/2 M1 R squared omega final. I feel like I'm running out of room here, plus just M2 times R squared omega final, because they're both stuck together. You can read it. And then I think there's a R in every single term, R squared. So divide both sides by R squared. And I end up with m1 over 2 omega initial equals m1 over 2 omega final plus m2 omega final. I'm going to solve for omega final, which is what we're asked for. So we've got 2 over 2 omega initial is equal to 2 over 2 omega final plus 1 omega final, 1 plus 1. So omega final equals omega initial divided by 2. So I'm not even going to convert. It's 200 RPM, which is not an SI unit, but I can divide it by 2 and say omega final equals 100 RPM. I think. Okay. And then the last thing, how much time we have left? We got some time, so we can do this gyroscope thing. I got a lot of questions last night about this gyroscope. Let me leave that for a sec. I will scan it tonight. See people taking pictures. Yeah, so this was this reading. Unclear on exactly what is the difference between big and little omega in the case of the gyroscopes. I'll talk about that. Again, right-hand rule, gyroscope and precession. Confused about the spinning gyroscope. Why doesn't it fall? Et cetera, et cetera, et cetera. So let's go over this really carefully. And I've got some, there are some end of chapter problems, the passage, rate of passage problems or something at the end of this chapter, and chapter 11. I'll go through some of those. So, idea is that you have a spinning disk, and the disk is spinning in a vertical plane. So, example, if this was tilted up, it's spinning something like that. And it's supported only at one end of its axle, as shown. If you let it drop, you would expect it would just fall over. So if it wasn't spinning, you let it drop, boom, it does just fall. Gravity exerts a torque on the center of mass. It comes up and grabs at the center of mass. The torque is going to be R cross F. F is down, R is this way, so it's going to be into the screen, I guess, in this case. And then that's going to create an angular momentum, which is into the screen. I times omega is into the screen, so it's going to rotate, I guess, clockwise. So it does. So it's very simple, if it's not rotating. But instead, the axle remains horizontal while the whole thing goes goes rotating around. So you spin it, you let go, it does that. Kind of weird. And the other thing that too is that you can feel this if you are the person holding the thing, twisting, and you try to twist it, it feels really screwed up. It goes the wrong way. You twist it this way and it goes up. So there's something very messed up about something that's spinning. So we're going to go over why it does that. This is called precession. There are two frequencies going on here. One is the spin frequency, that's the little lowercase omega, which is really fast. It's a high number of rotations per second, or 2 pi's per second. And then there's capital omega, which is called the precession frequency. It's much lower. It takes about 1,002, 1,003, 1,004, 1,000, about 5 seconds for it to go 2 pi all the way around. So it's a pretty small number. And it's right here. Here's a way of deriving it. Derived in the textbook. Precession frequency, capital omega, is m times g times d divided by I times little omega. M is the mass of the gyroscope, I is the gyroscope's moment of inertia, and d is the horizontal distance of the center of mass from the support point. What were you? Hey, Kevin can do what he wants. He's in charge of safety here. He's the reason I haven't killed myself over all these years. So, okay. Angular velocity of the spinning gyroscope is assumed to be much, much larger than the precession frequency. So the only way you can derive this is you have to do an approximation where little omega is much, much greater than big omega. And so we can go through all that math, but I think what I want to do is just try to at least visualize things in 3D. And so we're going to do the last 3 problems from Wolfson, or 3 of the last 4 problems from Wolfson. Okay, so here's a gyroscope. It's spinning around. It's a little bit difficult to see on this, but it's spinning like this. So, where this goes behind. So it means that this is your omega vector is going in this direction. And it's also your L vector, right? This is equal to L vector divided by I. So the L vector is some big vector that goes off in this right direction. If you push on this shaft between the arrowhead and the disc, so you put a force down like this, which we can call F push or something, then this arrowhead will move either away from you, towards you, downward, upward. Okay, so it's a bit hard to visualize. So what I'm going to do is redraw the whole thing from a top view. So let's do top view. The only way I can picture that. I'm going to use that same idea that a circle means it's coming up at you and an X circle means it's going down. So here's the non-spinning weight. Here's that shaft. Here's the stand, so there's the pivot of the whole thing. And then here's this spinning, whatchamacallit. So it's going now like this. I can't draw things in 3D because I'm a terrible drawer, so I just draw everything in 2D. So that's the big spinning disc. And this big spinning disc, drawn in blue, has a big L vector going this way, L, because it's spinning. And then what happens is we're going to apply a force here, which, maybe I'll draw in red, which is down. So this is into the page, F push. And it's going to have R vector, like this, R push, from the pivot. So the torque from this, torque push, is equal to R push cross F push. So that's going to be R cross down is going to be up. Okay, that direction on this diagram. And then what you do is remember that torque, I guess push or something like that, is going to be dl by dt. And so it's approximately equal to the delta L divided by delta t. And so delta L, which is going to be a small little change in your angular momentum, is going to be in the direction of tau push, times delta t. And that's going to be, I guess, delta L is much smaller than L, because it's a little change. So what it's going to do is going to be like this, delta L. So it's going to take this spin vector and now turn it a little bit this way. So this whole thing is going to go, do I have this right? Make sure I got it right. There's something a little wrong with this. F push, R push. Yeah, this is what's wrong here. Okay, so I've got this pushing horizontally away from you. I think I've drawn that wrong. So this push vector, sorry, I've completely messed up this whole problem. So this would be right if you were pushing down, like gravity would push, then you would turn this way. So, sorry for the dog's breakfast here, but this now pushing force is this way. Does that make sense? you're looking top view, you're pushing away from you in this diagram, so this is your F push. I used to have a professor that claimed to do this on purpose. He was teaching electromagnetism from Jackson. It was a first year grad course in electromagnetism. And he would fill up the board and he'd get the wrong answer. And he'd fill up like 5 boards of all these equations. And then he'd say, "Oh dear, I've made a mistake." And so the whole class would get really engaged and try to find, where did the professor make his mistake? And it was really fun, but anyway. It is a teaching technique, so I could say I did this on purpose. Anyway, so now, let's do it again. R push, cross F push. Now it's coming up out of the page. So, there's your F push, R cross. Now, this is the answer. I think that's better. Makes sense? Because if in the top view, in this diagram, if the force is this direction, then this will be the tau push. And then what that does is put your delta L up out of the page. So there we go. So it goes upward. Makes sense? The point is that since there's already a very, very big angular momentum vector L, the torque just changes its direction a little bit. If it wasn't rotating and L was 0, then it would just, all the angular momentum would be in this direction and it would rotate the way you're trying to turn it. But since you've already got that big vector, you change the direction a little bit and it's not what you expect. Let's do one a little bit better. Maybe I'll scan my 5 p.m. notes so that they're not quite as messy. 66. Same thing. Let's do, if you push on the shaft between the arrowhead and the disc, pushing directly upward on the bottom of the shaft, let's try that. So here's the disc. Here's your big L vector. Here's the pivot. You are pushing now, this is top view, pushing directly upward. So that is now going to be like this, F push. Here's your R push. The torque of the push is R of the push cross F of that push. So R cross F now is, it's hard to do that with my hand, but it's down like that. So delta L is down. So it's going to come towards you. Makes sense? B. It'll go kind of this way. And then the next one is, what if instead of a quick little push, you have a constant torque due to gravity? This is 1167. If an additional weight is hung on the shaft, the left end of the shaft, what will happen to the arrowhead? So again, top view. You have now, here's the pivot. Here's that big spinning disc. So you have angular momentum of the system, L initial or something is like that. And then you have into the page your F of the weight that you hang on there. And the vector of that, I guess the R vector of the weight, is now to the left. So again, right hand rule. R cross F is down. So torque of this weight is equal to R of the weight cross the F, which is into the page, and you get that it's this direction. So what that's going to do, this will be your delta L, which is going to add to here. A little hard to picture it, but since this is your original I vector, then when you add that delta L, this will be your final, a little moment later. And then you can imagine that'll move the weight, so it'll continue going all the way around like that. And that's exactly what's happening with this. Originally, as I spin this thing, let's spin it this way, for example, then the gravitational torque, so right now I have angular momentum vector which is pointing way, way out towards the right. So I'm going to add a little torque from gravity, which is going to be R across the mg, which is going to be into the page. So if I let go, it wants to go into the page. Make sense? I can spin it the other way, whoops. Let's spin it this way, like that, so that now I've got an angular momentum vector which is going way, way, way out towards the left. Again, torque of gravity is going to be R across the mg is down. It's going to be into the page, so it's going to rotate it that way. Okay? That's what brings it around that direction. So that's why it's processing. Okay. You guys are very patient with me. I will mention that you may have heard of NMR. You go to the hospital and get an MRI. What you're doing is it's magnetic resonance imaging, so it's nuclear magnetic resonance. What happens is that if you have a proton is spinning, just like this, and you put it in an external magnetic field, a very strong static magnetic field, then it's like you apply a torque to it. And instead of just rotating the proton, it causes it to precess. So the spin of a proton is very, very high. It's up in gamma rays, but the precession frequency is much lower. It's in the radio waves. And so if you now have a proton which can interact with radio waves, you can flip it one way or the other and use radio waves, which are totally harmless to a human body, to investigate the protons and what their environment is like. So you can use this to image the inside of a body. Some restlessness, so I'll say before Wednesday, please read up on chapter 12, static equilibrium, or at least watch this pre-class video. And if you're on the diving board, what are the directions of the force on the board at point 1 and point 2? I'll talk about that on Wednesday. Thanks.